Stanford University.
Good afternoon. Welcome to the last EE380 of the spring quarter. I thank all of you for attending. The students, I hope you've all received the email about evaluation forms describing how the registrar will do something wonderful for you if you do an optional evaluation form and how bad things happen if you don't do the required ones. I think that many of you have missed out though by choosing the video option, but most of you who managed to finish the class will be watching this during dead week and wishing you got that hour back. Sucks to be you. I mean, seriously, it's easier to keep up and do it in real time, but you're not going to listen now. We conclude this quarter with sensors. Sensors don't get a lot of attention, at least at Stanford, which is sort of unfortunate because they're really one of the harder problems from a standpoint that we don't really care about. We don't worry about computers having to be in crappy conditions well, there's a few people who worry about low power, but when they talk about low power, they talk about a cornucopia from the sensor people's point of view. Sensors also have to work in addition to low power and worse conditions, they have to be free. And the closest thing we have is a cache transistor with a whole bunch of other stuff around it. Whereas sensors have to be free in the onesies, and then they want to spread them everywhere. And that's going to be an issue going forward, but let's not get into that. As the world becomes more and more wired, sensors are going to become more and more common. I don't know if they'll ever be as common as beetles, but they'll certainly be more communicative. Today's speaker, Andreas Terzis from Johns Hopkins, they get upset if you leave off the S, will tell us about some of the problems and solutions in sensor networks.
Great, thank you for the wonderful introduction. It's a pleasure being here. So I will talk about some problems in wireless sensor networks. And let's see. So this is the outline of my talk. So I will actually use three applications that we are working on at Johns Hopkins to motivate some of the problems in wireless sensor networks. So I will start with our habitat monitoring application that we've been working on for a few years now, and then use that to motivate our work on ultra-low duty cycle data gathering, and also our work on data-driven time synchronization. Then I will switch to a system that we built to actually monitor the environmental conditions inside the data center, and I will use that application to motivate our work on contention-free data collection. And last but not least, all coming from Hopkins, I will also talk about our work on using a mode technology to essentially do vital signs monitoring and use that to motivate our work on supporting mobility in sensor networks, which is something that we don't really see a lot, and quality of service. And hopefully we'll close with some future challenges. So, probably this slide is not necessary, but just kind of an introduction to what is a mode. So the idea is that Moore's law, another kind of maybe a direction of Moore's law that we don't really see a lot, is that not only it allows us to double the number of transistors, but actually allows us to keep the same number of transistors but reduce power. And based on that fact, somewhere in the late 90s, we were able to build this essentially complete little embedded computers that combined communication, computation, and more importantly, sensing. So here's an example of current, let's say, generation mode, something called the T-mode Sky. And so you see basically it becomes fairly obvious that the resource constraints that we have to operate under. So it has a 16-bit microcontroller that runs at 4 megahertz. and then it has 10K of RAM and 48 kilobytes of ROM. It has a little radio that operates in the same frequency as Wi-Fi, but it has a maximum physical rate of 250 kilobits per second versus the megabytes that Wi-Fi has, and it has also 1 megabyte of onboard flash. Now, the trade-off here is that we have these extreme resource constraints, but the power consumption can be in the, let's say, tens of milliamps at 3 volts. So now it becomes actually feasible to operate using batteries for some amounts of time. What makes sensor networks interesting is that you can actually connect a wide variety of off-the-shelf sensors, either digital or analog, to these platforms. And basically, then you can have these what we call wireless sensor networks that effectively combine sensing, communication, and computation at small packages and large scales. So the premise here, and then this David Kahler coined the term macroscope, is that you can deploy these systems in the environment and monitor or observe phenomena that was previously very difficult to observe or even impossible. So in a sense, wireless sensor networks become this a piece in this infrastructure that observes the physical world and essentially, and then hopefully eventually actually actuates or changes the physical world. So we believed in that premise. So our first attempt was actually a system called Life Under Your Feet, which is essentially a collection of sensor networks that are built to study the effects of abiotic factors, things such as soil temperature and soil humidity on essentially animals that live underground, things like millipedes, worms, but even turtles. So to give you some examples of some of the research questions that a system like Life Under Your Feet is built for, so we know that concentrations of animals are very patchy, and there is a hypothesis that this patchiness is really driven by a spatial heterogeneity in these abiotic factors. So some parts of the forest are more wet or warmer, and these basically drive animals to those areas. But the point is that in the past it was very difficult to actually test that hypothesis because someone would have to go and collect this data manually. Another example is that in Maryland and actually in all of the eastern seaboard, there is a certain species of turtles called the eastern box turtles who do not have sex chromosomes. Instead, their sex is determined by the incubation temperature, and 2 degrees Celsius determines whether this is going to be a boy or a girl. And biologists worry these days that due to global warming, this essentially balance of the turtle species will actually be overturned, right? So again, we can use a system like Life Under Your Feet to monitor the essentially conditions at turtle nests in situ. A much bigger problem that we are starting to look at is the contribution of soil in the global carbon cycle. So in terrestrial ecosystems, soil is the largest consumer but also the largest producer of CO2. It produces about 10 times the anthropogenic CO2, the CO2 that we produce. The good news today is that this basically it also consumes 10 times it sequesters 10 times the CO2. However, the biological and microbial processes that generate the CO2, break down organic matter and generate CO2, are accelerated by temperature. So with global warming, there is a concern that essentially we will have a nasty positive feedback loop where actually more and more CO2 is produced. So now we can actually put CO2 sensors in the forest to actually understand what will happen in the future. So those are some of the science questions that we are trying to answer with a system such as Life Under Your Feet. Now, the architecture of Life Under Your Feet is fairly simple. We have modes that periodically collect samples and store them in their local flash. And then we have a gateway that periodically again retrieves the mode's measurements. And there is a database that stores all the raw measurements and all the derivatives, the data products of the data that we collect, and also the data provenance. So if there is something that goes wrong and potentially we do a calibration in not the perfect way, we can go back and actually reapply a better calibration curve on the raw data, so we don't really lose anything. So habitat monitoring applications such as Life Under Your Feet, or Life Under Your Feet is an example of a habitat monitoring application. So they share a common set of requirements. We want to reliably extract all the data, so scientists, the whole purpose of deploying these systems is to actually collect the data, and therefore scientists really don't lose anything. And they need to be deployed for fairly long times to actually capture these yearly environmental cycles and support networks that are medium scale, about let's say 100 modes, and that are sparsely deployed. So it turns out that we, at least right now, we have not really reached the point where we can actually kind of randomly spread these very cheap modes in the environment. It turns out that they are fairly expensive, and moreover, much of the expense is in the sensors themselves. So in a sense, we are still going to have a relatively small number of modes that are going to be deployed in a way that tries to capture the maximum amount of spatial heterogeneity. So you're gonna most likely, for some time to come, have sparse networks. Now, moreover, in many cases, we operate in the forest under multiple layers of canopy, so solar power is not really an option for us. So we are battery operated, and then we therefore, in order to achieve those essentially deployment lifetimes, we need to operate at very low duty cycles. And here, duty cycle is defined as the the percentage of time that the mode is active versus the percentage of time that the mode is active. And at least for the applications that we are looking at, the largest consumer of energy is the radio. So basically what we are trying to do is turn off the radio to conserve energy. So this is energy efficiency is a core problem in sensor networks, and many people have looked at that. So one of the most efficient protocols out there is a protocol called Dozer. And what Dozer is a protocol that does essentially data collection over a routing tree, a multi-hop wireless tree, using duty cycled modes. So what you want to do is that obviously you want to turn off your radio so that to conserve energy, but then you want basically when you want to transfer data, then you want essentially that the other your neighbors' radios are also on to basically to send data. And there are different ways of doing that. What the Dozer does is that it implements a TDMA scheme, a time division scheme, such that nodes actually synchronize their on times so that we can actually kind of keep sending data towards the root of the tree. Now, on top of that, Dozer also implements hop-by-hop reliability to achieve essentially the reliable transfer, end-to-end reliable transfer. Now, rather than implementing a network-wide TDMA schedule where all the radios are on at the same time so that the nodes can send data upstream, Dozer really implements, essentially synchronizes the schedules of nodes in a local neighborhood. Specifically, each node follows two schedules. One provided by its parent. So basically, I need to be up when my parent is up so I can actually forward my data to my parent in the tree. And one that I define for my own children. So I tell my children, when I will be up in order to, and so they can also be up at the same time so that they can send data to me. So you see, this is exactly the case here, where you see we have a parent that has 2 children, and then the gray area is where basically when the radios are on. So the parent actually uses periodic beacons to keep its children synchronized, and then later on a child wakes up, sends data to the parents, receives an acknowledgement. It can send maybe a couple more packets, and then the other child wakes up at a predetermined time to send its data. Yes.
Are parents persistent?
Parents. Dozer tries to keep the parent persistent, but then it actually has. If let's say my parent fails, then essentially what I can do as a node is that I can stay on for some amount of time, so that I can hear beacons from other nodes, and I can essentially select another parent.
Because it seems like, according to the battery criteria, parents will die quickest.
Yes, so that is a very good observation. Nodes that are closer to the root eventually essentially have to relay data for other nodes, and they will essentially die first. So that's in a sense kind of a limitation of all these three routing protocols. But that's a very good point. Any questions so far?
Yeah, what kind of beacon do you use?
So these are basically radio. So we use the same radio to send little messages. So at the beginning of the let's say our schedule.
So how many beacons?
They send one beacon per, let's say, period of let's say, I don't know, seconds. Defined. Let's say we have a essentially schedule that is 1 second long, and then.
Beacon is not an entity; it's a.
It's a radio.
It's an event.
Yes.
Okay, thank you.
Okay. Okay. So now, so Dozer does a very good job, and then it actually can achieve these very low duty cycles that we are looking for. However, duty cycle protocols, duty cycle routing protocols such as Dozer, increase the size and the complexity of the mode of the code that runs on the mode. So those of you that have written code for modes know that this is always a big concern. And so where does this complexity come from? So you need to synchronize with your or the neighbors' sleep schedules. You need to collect and disseminate these neighbor link quality estimates, and then run this distributed best path selection algorithm. Now, this complexity, doing all this, not only increases the complexity of the code that runs on the mode, but actually modes expend considerable energy to maintain this persistent routing state. In other words, I need to remember who is my parent, and I need to remember who are my children, so that I stay consistent with them. And so what do I get in return? I get a network that is constantly essentially available, so that when I have data, I can very quickly send it back to the gateway. Now, however, many applications, life under your feet being one, don't really require real-time access to the data, right? So the claim that we make here is that maintaining this network that is always on can be too expensive, right? So you're spending all this effort and energy to maintain a network that is always on, and maybe that you don't really need to do that. So a system that we built called Koala actually follows a very different approach. So nodes sleep on their own schedule, right? So they're not really synchronized. But what the gateway does is that it periodically wakes up the whole network and then downloads data from each node sequentially. So it basically wakes everybody up and starts downloading data from each node sequentially. And then once it's done, then it puts the network back to sleep. Now, from an architectural perspective, what we are doing is basically, it's the gateway that controls what are all the paths that will be used. So, from an architectural perspective, what we do is that we separate for the networking folks here, separate what we call the network control plane from the data plane. That is, routing is really implemented at the centralized routing at the gateway, and modes don't really understand anything about routing. The only thing that they know is that how to send data to the immediate neighbors. So the modes only keep forwarding state saying, okay, how do I send data to my neighbors? And then we implement a network-wide routing plane at the gateway. Now, yes.
How do you wake them up?
So that's the question, right? So how do I wake them up? So so I'll explain in the next slide. Now, before I do that, let me argue about what are some of the benefits of this approach. First of all, it's easy to see that we reduce the complexity of the code that runs on the mode, and as I will show you later, the energy consumption. We also have, because we actually kind of lay out these paths at the gateway, or the gateway decides how these paths will be, we have the potential for network-wide route optimization. So the gateway can actually schedule how these downloads will happen, so that it improves the efficiency of the downloads. Another thing that we found is that this scheme makes it very easy to implement any source routed routing essentially algorithm that you want, even after, or routing policy, even after the system has been deployed. So for example, we have been running our system for a few months, and then we observe that basically we are doing downloads in a certain way that, as you were saying, maybe is taxing some of the modes more than others. Now, once we can decide that maybe there are alternate paths that maybe if you're looking at basically, let's say, best path in terms of number of transmissions, total number of transmissions, we can have an alternate path that potentially offers a little bit, is less optimal, but it allows us to use a different set of modes. So in a sense, balance the energy consumption. And implementing that is trivial, because we don't really have to change anything on the code that runs on the modes. We just implement it at the gateway, implement the logic at the gateway, and then the gateway tells the modes how they will do their downloads. So that's another benefit of this approach. Now, to answer your question, as you said, correctly pointed out, the challenge is that since these guys are waking up and going to sleep using their own schedule, how do I wake them up? So the way that we do that is that basically each mode, when it wakes up, it sends a probe, it uses its radio to send a broadcast probe saying, should I stay up? If it doesn't receive an acknowledgement, then it goes back to sleep. Okay? On the other hand, if it does hear an acknowledgement saying, please stay up, what it does is that it stays up, and then it starts responding to other nodes' probes. Okay? So then if it hears somebody else asking, should I stay up, it says, please stay up, and then basically they stay up. So what happens is that when the gateway wants to do a download, is basically it starts hearing these probes from the nodes that it are directly connected, or it can directly hear. So it tells these nodes, please stay up. So these nodes now stay up, and then they actually hear some other nodes that the gateway cannot directly hear. So now these guys stay up, and eventually the whole network wakes up. At this point, the gateway starts collecting what we call neighborhood information. So it actually learns who can talk or who can hear whom. Okay, and then what it does is that it actually overlaps the data collection part with learning the full topology of the network. So there are some nodes that it can hear directly. So it says, okay, I want to download data from you, from you, from you. And by the way, as I'm downloading data from you, also tell me who are other nodes further away that you can hear. So now I have downloaded data from my immediate neighbors. The gateway has downloaded data from its immediate neighbors, but it has learned another piece of the network, and then it can download data from them sequentially, and so on and so forth. What we do in reality, rather than learning the full topology of the network every time, we optimistically assume that the topology remains constant, from the last time that we tried to do the download. So in the beginning, we try to actually use that topology to download data. If it doesn't work, then we go back and actually learn what are the conditions right now. And then the gateway sequentially collects data from each of the modes. Once it's done collecting all the data, then it essentially the network by its own goes back to sleep. Okay, and here I failed to mention is that we are also taking advantage that we have flash, so nodes can collect data using their sensors, and they just write it into flash, and then some hours later, when the gateway wakes up, and then they can actually download data from flash. Okay, yes.
So if you were to eliminate the network and simply collect all of the information in flash, and pick up the flash memory when the batteries run out, don't you have a much better system?
So this is a good question. So it depends on who has to go out to pick up the modes. I said that we don't really have that delay limitations, right? So in a sense, we don't really want to wait a few months to collect all the data, right? So these days, so I think Deborah Estrin actually made a very good observation. So the best reason for having a wireless network is to know when your nodes have failed, right? So in a sense, we actually use that as essentially, are these guys still alive, or basically have they failed? We need to go out and change them, replace them, or something of that sort. Yes.
So far, it's sort of been assumed that the nodes are roughly stationary.
Yes.
But they're small enough to attach to turtles. And turtles don't go very far.
Right.
How far do turtles go?
Turtles actually walk long distances, right? It just takes them a while, I guess. Right. So I mean, depends on the time of the year, and also basically foraging patterns and things of that sort. Now, our modes actually are not on turtles. They are, kind of static next to turtle nests, or in different parts of the forest. So far, this is a static network. So yes, so we're not looking at mobility right now, I guess. Yes, Bran.
Going back to your claim that the best thing about the wireless is that we know that nodes fail.
Yeah.
If you wanted to have that could be implemented much lower power, right?
That they fail, or that?
Yes. You wouldn't have to transmit all these huge data packets.
Right.
And then plus another thing which you didn't mention is that someone eventually needs to pick up those modes, otherwise you are polluting the environment.
Yes, eventually we will go and pick them up, right? And we want to reuse them too. Yeah. So today, to go back to the when things break, we actually collect 2 to 3 times more metadata than data. So we actually essentially log everything that happens on the mode, and we use that to actually as metadata that we collect. So how many times we have taken samples, how many times we read into flash, what is the battery voltage, what is the regulator voltage. So we collect all this data, and then we record that. Yes.
I think also, failure does not necessarily mean node dies, right? It can be that there's a short, it can be that there's something wrong with the sensors. The only way you're going to know that is if you actually see the data.
Right.
Now, whether you could perhaps send a summary of the data or a subset of the data, but I remember for the Redwoods deployment, right, there were nodes that were disconnected from the network, and those nodes lasted 3 months, and they ran out of storage. You're not going to climb the tree to get them, because then they're going to be a different position. There's not the same sampling.
Right.
Whereas nodes that were able to report were able to last 6 months, 9 months.
Right,
Because they weren't constrained by their storage.
Right. Yes.
So going back to the wake-up scenario,
Mm-hmm.
there's a certain amount of overhead associated with this. So have you done any analysis on what the limit is, where you reach the point if you wake them up too often, you're actually losing more energy than you're saving by doing this?
This is a great question. So here's basically, as you correctly pointed out, there is an inherent trade-off between essentially, or what you can do is that you can trade off latency. In other words, you can essentially wait until the modes have actually collected more data and do one big download. And by doing that, you are actually essentially amortizing the cost that you have to pay to wake up the whole network. So rather than waking up the whole network many times and doing small downloads, you wake up the network once and then you do a big download. Okay? So then this graph actually shows you, quantifies that trade-off for the benefits you get here. So on the x-axis, we have data rate in terms of how much data every mode collects per day. Okay? And the three different lines that you see are actually chunks of data that you can collect. So you can basically say, I do my downloads, 32 kilobyte downloads up to all the way down up to 500 kilobyte downloads. Of course, you have to wait until the modes have actually collected this much data. But by doing that, actually, you get much different duty cycles. So you can actually, with a system like Koala, we can actually explore that trade-off or the space of saying, okay, I can wait a little bit longer, and by doing that, I can actually increase the lifetime of my network. And this gray box here is the duty cycles that reported by Dozer. So in a sense, depending on, so they can do something like 0.2%, or they were claiming. We can actually be more efficient than a system that does essentially this very tight synchronized data gathering. Yes?
So what's the percentage of the energy that goes into the radio as opposed to the computation?
For a system like this one, you can pretty much say that it all goes to the radio.
So it's to your advantage to do as much of your data processing at the mode as possible.
Yes.
And actually provide it with much greater computational capability than you might otherwise do.
You're right. Now, when you go to the domain scientists and say that, they say, thanks, but no thanks. I want all the data. I don't really want to, there are all these things about in-network processing, which, obviously can have huge benefits. But they are saying, no, I want all my data. And if I need to go and change batteries more often, I will do that. But I cannot really, as long as it's feasible, right? I mean, you reach a point where at that point, you don't really have the capacity, the network capacity to offload all the data. But until then, they are not really interested in doing all these essentially trade-offs.
Well, what happens when your network of sensors becomes somewhat larger, say 100,000 or 1 million nodes? What do you do?
Well, I mean, if it becomes 1 million nodes, right, so you can always divide and conquer, let's say. So, you're not going to have a network of 1 million nodes that there is a single network. You can actually, at that point, you can kind of divide it into smaller networks. But there are definitely limitations of this approach, where you cannot really say, I'm going to have essentially single network with millions of nodes, and then I can expect to run protocols like Koala. So there are definitely limitations to this approach. Yes.
Okay, you do a wake-up cycle, and once you, you're not distinguishing between turning on receiver and turning on transmitter.
Right. So the radio is a transceiver, so it's both a receiver and a transmitter.
Right, but normally transmission is a lot more expensive than reception.
Actually, for a low-power radio such as ours, reception is more costly than transmission, believe it or not.
Given those economics, then there's the problem that as you wake everybody up, you're basically telling all your immediate neighbors to go on receive. Will you wait for the other ones to randomly come around to their transmit time slot? How often do they retransmit in their idle state?
Sorry, what do you mean? How often they? I wake everybody up, and now they are what we call idle listening, and basically there they are essentially consuming more power than if they were transmitting, right?
No, before you're in the idle state.
Uh-huh.
How often is each node going to wake up at that point?
I see. So so basically let's say we do, let me see, once every 20 seconds.
Okay, which would mean basically that for each ring as you expand outward, it would take you an average of 20 seconds, and probably you'd have to double that because you might miss a transmission or something.
Well, I mean, I guess on the average you have to wake up 10 seconds, right? Or in the worst case, 20 seconds to wake up every, as you said, every level or ring of the network. Yes.
Okay, so then a whole cycle would be 10 or 20 seconds times the
diameter
of the network in some sense.
Right.
But that means that you're waking these things up for, if you have a network diameter of 5, that you're keeping these things awake for a full minute, but you're actually using only an infinitesimal percentage of the data transmission time available.
Right.
So having woken everybody up, do you then synchronize everybody's clock so you don't have to do this again for a while? Or?
We don't, right? So you could potentially do that, right? But then you're kind of saying, okay, now we're going back into essentially having to make sure that we are staying synchronized. Right, so or we have to wake up at the same time. So basically, the claim that I'm making here is that this, which seems potentially very inefficient system, right, by doing essentially few large but infrequent downloads can be quite efficient, which might seem initially counterintuitive.
Okay, but having done a poll process that takes a minute to achieve a 0.1% duty cycle, you now have to stay down for 1,000 minutes. Is that right?
Well, overall, but the point is that, you know, in order, right, to collect 500K of data, right, you will do these downloads very, very infrequently. So overall, essentially, you will spend the vast majority of your time, you spend it sleeping and then sending these very small probes. And therefore, you amortize the large potentially cost, essentially waking up the whole network and doing the download, but you amortize it over a very long time that you spend sleeping.
Okay, but that basically means you wake up these things about once or twice a day.
Yes.
Oh, okay.
Yes.
That makes more sense.
That's exactly what it means.
Okay.
And it's okay to do that, right? Because, you know, yes.
You might be starting to slow down, and you might be kind of tight on time.
Okay.
You've got 3 things to.
Yes. Right. So you know that is that is definitely a problem that it has happened before. Now, so you know this is a system that we have deployed. So we have 3 active locations, about 100 modes total. Our biggest location is in this urban forest outside of Baltimore called Cobb Hill. This is a system that has 50 nodes. It has been deployed for almost a year. And I told you these are some of the science questions that we are trying to answer. The gateway is over here, and then you see that this network is kind of this elongated pattern, so that we see that we are actually taxing these guys more heavily. But so we are seeing what maybe we can actually do something with the download. So this is the amount of data that we have collected. So this is actually over a little longer than 3 years. You see actually our different deployments are up there. We have collected about 40 million data points. This is not really a huge number, but at least it shows that it's a real system that actually collects data. About 180,000 sensor days. So with the amount of data that the sensor collects a day, and then you see kind of also our different generations of data or of networks. These are the first deployment. It took us a while to build the second generation. So that's you see the curve is flat, and then essentially another with the current generation of deployments. So so let's see. So we have until 5:30. So I may skip this timestamp reconstruction to go to talk about the data center stuff. So let me skip that. So yeah, I'll skip it. So, it took us 3-4 years to collect 40 million data points. So here's a network that collects 2.5 million data points a day. So this is a network that is deployed to actually monitor the environmental conditions inside the data center, and this is something that we do with our partners at Microsoft Research. So this is the DC Genome project, and or data center genome, not our name. And the motivation is really to understand how heat is generated and transferred inside the data center, and with the ultimate goal to improve the efficiency of the data center. So what we collect right now is mostly temperature data. So here's our data from 20 sensors deployed in our data center, really a server room at Hopkins. And basically you see, as I said, 20 sensors deployed across different racks. So then basically we have anywhere right now between 3 and 5 sensors per rack. Essentially in our data center at least, the cold air comes from the bottom, and then you see the sensors that are deployed close to the bottom basically are the colder ones, and then the sensors that are up are the warmer ones. Here you cannot really see, but there is actually a 15 degrees centigrade difference between the bottom and the top of the rack. Anyone has an idea what are these little squiggly lines? Kind of patterns of temperature going up and down fairly quickly. This is 1 day. It's the AC coming on and off, right? So it's essentially right here, the AC coming on and off. So temperature goes on, goes up, and then the AC goes on and then goes down, and so on and so forth. Here, basically, servers are idle. So then, basically, yes.
Generally, the lines higher up are servers that are higher in the rack, and the lines lower.
Right.
So why is there that inverse relationship where when nodes at the bottom heat up, nodes at the top cool down?
Very good question. So great. So I'll tell. So we had the same basically saying, well, what's going on? So basically, you see that basically, let me see, where is it? Right over here, right? This guy, right?
The
The
bottom ones
temperature.
get really hot, and the top ones get cold.
What happens is the following. In the AC, you can actually control the fan speed. So basically what happens is that in some cases the AC increases the fan speed, so cold air starts shooting up with higher speed. Okay? Now there is something called the Bernoulli principle that says higher basically air or any essentially gas at higher speed actually creates lower pressure. So what happens at the bottom of the rack, you have essentially low pressure, and then hot air from the back of the server gets sucked in the front. Okay? So basically that's why, and then this cold air quickly rises, loses speed as it rises, and then it cools up the higher part of the rack. So yeah, you get this very interesting essentially artifacts or that we didn't really know. The good thing is that actually this has changed so you can say go to dcgenome.cs jhu.edu, and this is basically data from right now we will have 120 sensors on our cluster, 3 to 5 sensors per rack, both in the cold aisle and the hot aisle. Okay, so that's what we want to do. RackNet is the system that we built. It includes both these modes called genome modes that are essentially, you see, they are essentially, this guy obviously has a radio, but this guy does not. And then basically the modes in the same rack, one of them has a radio and the others don't. So basically we use cables, USB cables, to both do the data extraction, but also to power. Interestingly enough, for a project like DC Genome and RackNet, power which is a huge concern for sensor networks in general, is not an issue. Okay, so now you have as much power, well, not really as much power, but at least it's not really an issue. What becomes an issue is network capacity, right? Because you can very easily deploy a very large number of modes in a relatively small area in order to get the sensing, essentially fidelity that you want, and now you have a very large and very dense network. Okay? Yes?
Going back to the question of why wireless, why not simply build a sensor and connect it to the servers? You have essentially the equivalent of a wireless connection.
Right. So, so I was talking to Maria earlier today, and we basically the idea was that let's put an Ethernet cable on every little of these guys. You quickly run out of basically the patience of the network operator saying, "Oh, it's you again. You need more Ethernet ports, right?" So in a sense, it in all seriousness, it complicates the deployment strategy. Right. With a server, the people in the data center are very particular in what software runs on their servers.
But if you're going through a USB port, you're running software on their servers.
No. So interestingly enough, they are so essentially paranoid that we actually cut the little cable, the data cable on the USB port, so that the server does not even detect that there is something connected on the USB port. So we just basically are sneaking in there, sipping in a little bit of power, and that's the only. So they don't even basically can see that we are connected to them. But I mean, in another environment, maybe different set of constraints, different administration. Maybe that's not a problem, but definitely. In this case, it is a concern.
And how about interference?
One slide, it's coming up.
One other question then. One of the characteristics of the server farm is tremendous numbers of runways for cables. But cables are cheap. They're easy to put in place. Why not just cable them?
The racks in the basement, they don't want.
Not your particular system, but mine are very neat.
If you have.
I think if Andreas met you and said, "Could you lay down some cable for my wacky little sensors?"
Well,
there's a little more pushback. There tends to be a lot of pushback, right?
Yeah, but if you're buying enough racks, the cable's built in and the sensor's built in and all that stuff is built in. I mean, if you're plopping down data center after data center after data center, like 3 companies in the world do.
I guess from my perspective at least, we can hypothetically argue about this, but in the sense of the people who run Microsoft's data centers feel this way, right? And when Microsoft Research says to them, and they're not jokers, and they say, "Hey, we want to deploy this," they say no, right? And you got to respect that. You can try to argue, or you can just play the game.
Yeah. Well, we're going to get to the benefits here, and I'm going to ask.
Well, no, I don't know if we're gonna get to it. No, and it's not that we haven't really done much of the work on actually how we use the data, right? So we are starting. But back to your question about interference, right? So, we can have, as I said, quickly, very easily, a very dense network where we can have about 1,000 sensors in a colocation facility. And because they're so densely, basically imagine rack per rack, you can easily have 50 to 60% of those nodes in your immediate neighborhood, right? So you can actually hear 50, 60% of those. So if you look at the graph at the top, actually shows you the PRR, the packet reception ratio for these different links. So yes, about 50%, half of the links are perfect. They have, PRR close to 100%. But then there are still marginal links. So what I'm trying to argue here is that the routing problem is not really solved, saying that, okay, I can just randomly pick any link and basically it will work. So you still need to pick the good links. And this graph here actually shows you basically many of these data centers have 802.11, right? So 802.11 works in the same frequency range as our 15.4 modes. And here you see actually the different Zigbee channels 15.4 channels, and here is basically the noise floor. And so basically this bubble shows you what percentage of measurements actually fall into this noise floor. So you see basically that if you are on a channel that is used by Wi-Fi, then you get significant interference. However, there are multiple channels like 15 and 20 and these guys 25 and 26 that actually have no interference from Wi-Fi. So this gives you a potential to actually use multiple channels to increase the capacity of your network, right? So you can actually essentially do multiple downloads over multiple channels. Okay, so that's basically some of the data we collected from a data center, I should have said that, that shows you what are the challenges and what are the opportunities. Okay?
What noise produced by the servers themselves?
You know, if you look, so this is basically looking at basically just sampling the radio channel. So, you know, it's fairly quiet, right? So, you know, so it's not that bad. Okay. So, as I said, the main challenge here is that we have a potentially very large network, and then we want to reliably collect data from these sensors. So, to give you some idea, we are collecting data, taking these temperature measurements anywhere between once every 30 seconds, once every 10 seconds, depending on what is the use of this data. And then, you know, if you're starting thinking maybe I want to collect other types of modalities, power consumption, you may want to do it more frequently or more or less frequently. So the main challenge is really scalability, and you know, you want to reliably extract this data. So you might say, well, you just told us about something called Koala. Can you use something like Koala? Now, because you're collecting a large volume of data, going back to what you're saying, trying to do this basically centralized way where you wake up the network and then you figure out what the topology is, or collecting all the data to learn what the topology is, it becomes very, very inefficient. So you really, at this point, you want to have a distributed tree maintenance protocol. So you will create this tree to collect the data at one or more gateways, but you want to do the tree calculation in a distributed way. You know, now because the network is very congested, right? Actually, it tries to carry a large volume of data. As data starts trickling in closer and closer to the root of the tree, essentially these guys need to relay large volumes of data. So what will start to happen is this high load will create losses and also latency. So essentially is what we call congestion collapse, right? So essentially more data is coming and the different data flows are essentially competing with each other, and they are essentially corrupting each other. So what we will use is that rather than letting nodes transmit data whenever they want, we will actually coordinate how nodes actually generate the data. So we will do this coordinated collection. And by the way, we also use multiple channels. So we actually divide the tree into multiple channels. So we have trees that are actually operating at the same time over different frequency channels. So we can actually do multiple downloads over each tree. So now there are multiple benefits to what I call this coordinated collection. So you know, so the main, you know, again, the main challenge here is that we want to avoid congestion collapse under high load. Okay, so you know, there are multiple congestion control protocols out there, things like RCRT or IFRC. You know, for those of you that these acronyms mean something, you know, but congestion control, I argue that congestion control is not sufficient. So in a sense, waiting until the network is congested in order to actually react is a fundamentally difficult problem, because at that point, essentially it's easy to overreact, essentially try to slow down more than what you should. And once you reach that point and you try to react at that point, even your signals that you're trying to send down to this node saying, okay, please slow down, might actually essentially be lost. And essentially your system reaches an unstable point, and then trying to basically push it back from that unstable point, is a fundamentally difficult problem. What we do instead is that rather than trying to do congestion control, we will want to implement a scheme where we avoid or we prevent congestion from happening in the first place. And if you think about it, how does this congestion really happen? Well, this congestion happens because these guys start essentially transmitting on their own essentially schedule, and then as they kind of go closer and closer towards the root, they start interfering with each other. They start contending for the radio medium. So what we do instead is that we want to coordinate, actually make only one of them or only a single flow be active, end-to-end flow be active at any point in time. And the way that we do that is actually with a distributed essentially coordination scheme, which is nothing else than a variant of token passing, right? So those of us that are old enough, we remember what token passing is. Essentially have essentially this really token that goes around the network, and the node that collects the token can actually transmit data. And once this node has finished, then the token actually gets passed to the next node. So it's a kind of a retro networking approach. Now, another benefit of this approach is that, which is something that congestion control protocols struggle with, is that it removes the uncertainty of what really caused packet loss, right? So especially, and then many people have observed that, but in wireless networks, packet losses come from two sources, either really congestion or really just corruption because we are on a basically noisy network. Now, many of the congestion control algorithms basically treat loss as signal of congestion, and they basically scale back. Now, however, in a system that that there isn't anybody else, any other network flow contending with you, then you can essentially clearly, okay, packet was lost, this was because of actually noise or interference, and I can basically know how to react. So it kind of reduces that, removes that uncertainty.
Except for the case where you lose the token.
Exactly. Right. So this is a classic argument about token passing, right? So why token passing is so great? People show that it behaves, has very high efficiency under high loads and all this good stuff. But then the challenge is where, okay, all the complexity built into the protocol to make sure that when the token is lost and it's regenerated, and then not multiple tokens go over the network. So these are all valid points. The approach that we have here is then what is different is that we have this gateway that plays a very central role in the system, and then the fact that data is actually generated with a very normal pattern. So the gateway knows when it should receive back a token, and then it knows how to generate a new one if it's lost. Tokens also carry a sequence number so that you know whether you have basically multiple tokens or things of that sort. But but that's definitely a valid point. So I guess I don't really need to show you how this token passing idea works, right? So a node carries the token, or a node receives the token. When it has the token, it sends data upstream, and so on and so forth. The other trick that we play is that actually, okay, let me play through this thing. If we want to eventually make some data will be actually lost. So by actually having this token circulate, we also learn the topology of the network. So then when the gateway wants to download or to re-request some data that it was missing, it knows how to create the source route to actually talk to this guy. So basically, at this point, the gateway can, in order to recover data, sends a source route request down to the particular node, which actually can send the missing data. So there is that's another side benefit of learning the topology of the network. Any questions so far? Okay, so the RACnet or DC genome has been deployed in 2 test beds, in a data center test bed and 2 production environments. Each one is about 700 genome modes. A third of them are wireless, so something between around 200 wireless nodes. What I will show you here are results from a test bed in the data center, and I will use two evaluation metrics. One is the data yield, basically the average percentage of node data that is successfully received at the gateway. The other metric that we will use is something called IPI, for inter-packet interval. Let me explain what I mean here. Is that nodes generate data with a fixed frequency. Let's say one temperature measurement every 30 seconds. Now, if everything was perfect, you would expect that a new packet, a new measurement would arrive at the server every 30 seconds. However, as you start losing data, or as the network starts being congested, essentially the network is no longer a wire that basically kind of produces a constant delay, but maybe some data kind of spends more time in the network, so you will actually see this increase in the IPI, in the inter-packet interval. Right? So ideally, what you want to have is IPI equal to the essentially data generation frequency and data yield 100%. Okay? Now, what I will compare is that I will compare RAP with two other protocols. One is CTP, which is a best effort data collection protocol. It doesn't try to implement reliability. And the other is a protocol called RCRT, which stands for Rate Control Reliable Transport. So it's also a tree routing protocol that implements congestion control, specifically rate control. Now, now you see basically sensors sample at 10 seconds, so they produce a measurement every 10 seconds. And what I will do is that I will increase the size of the network and also the density of the network. So starting from 50 nodes all the way to 150 nodes, and these guys are deployed in the same area. Right? So by putting more nodes, I not only increase the size of the network, but I also increase the density. Okay? So you see that when the network is lightly loaded, essentially all the protocols do great. Right? So basically one sample is generated every 10 seconds and one sample arrives every 10 seconds more or less at the gateway. However, as the network size and density increases, you see that, for example, RCRT overreacts, tries to basically, as the congestion starts to happen, RCRT overreacts, and then essentially by slowing down the servers quite a lot. We didn't really run RCRT for 150 because effectively it didn't really work. Now, if you look at the 150 nodes, basically you see that RAP actually slows down actually a little bit. And actually, CTP does very well, but also the IPI increases by a little bit. Now, then, however, it's while the IPI in the case of RCRT increases because RCRT explicitly tells nodes to slow down, the IPI in the case of CTP increases because actually some data is lost. Right? So if data is lost, and CTP by design, it will not try to recover the data, then it will take some time. Basically, the IPI is until you receive the next basically sample. So here, I'm showing you the yields. So basically, again, when the network is lightly loaded or small networks, yields are 100%. But then, as we're starting to increase the density and the size, essentially, CTP essentially reaches, or the network, or CTP tries to push more data than the network can really essentially deliver, and then as a result, some of this data is lost. Okay? So which is something that you would expect because CTP was never meant to implement 100% reliability, and it doesn't try to synchronize the essentially the transmissions of the different nodes. But the point is that RAP can achieve the reliability that you would expect. Now, interestingly enough, RCRT, although it is supposed to really provide end-to-end reliability because it tries to essentially to push back the network after it's been congested. The gateway cannot even deliver its downstream request saying, please retransmit some of your data. So some of the data is actually completely lost. Okay, so that's those are the I guess the comparison. Okay, any questions? Okay, now
Now that you're switching,
I am switching.
you didn't talk about the benefits of actually collecting this data.
Yes, so there are a number of directions. First of all, we want to control. We want to, for example, understand how the actions at the HVAC, essentially setting temperature, or actually have. We want to create. The first thing we want to do is that create a very detailed heat map of the data center to make sure that no part of the data center rises above a certain temperature. That's number one. Number two is that if you know what is the temperature inside a data center, when a new job arrives, you might say, I want to start a new virtual machine at a server that is colder, actually colder than a one that is hotter. Even if you basically want to install new servers, you might say, where should I can put them in what is now the colder part of my data center, so I don't really need to essentially spend more energy. If I have a server that has many disks, where is the right part to put it inside a row of racks? It turns out that disks are very sensitive to increases in temperature, so you might worry that if you lose, at least temporarily, cooling, you want to make sure that you put them in a part of the data center that actually the temperature rises relatively slowly, rather than in a part that the temperature rises very fast, so that you're not going to harm them. So those are some of the potential uses, and we are really kind of exploring that space. Yes.
So there's also sensors connected to the air conditioning system.
Yes.
So are you trying to connect this network to the air conditioning system also?
So the air conditioning, the HVAC, actually, many of the more modern HVACs actually, offer network connectivity that you can actually remotely, essentially read that data from the HVAC. But the point is that the HVAC is one point over here, and then you have thousands and thousands of servers at all other points in your data center, right? So you really need to understand, looking at the temperature at the HVAC doesn't really mean that
Doesn't the HVAC also have sensors all scattered around?
No, not that I know of. Maybe a few, but definitely not on every rack, right? And I showed you that even if you look at a single rack.
But I'm saying, can't you feed the data from your system back into the HVAC?
Yes, I mean eventually, right? You want to essentially understand what the temperature is right now to better control the HVAC, right? So that's the other dimension of efficiency. Okay, switching. 5 minutes. Yes. So being at Hopkins, I have to do something with healthcare. So what we do is that we actually build these little modes that actually we put on patients inside at the waiting room of the emergency room at the Hopkins Hospital. So this is a nurse, but the idea here is that, or the motivation is that we need to track vital signs of patients in both structured and unstructured clinical settings. So, for example, if you ever visited an emergency room, if you go there and if you're not really in very bad shape, you wait for many hours, right? And then there is at least anecdotal evidence that during that time patients deteriorate, and but nobody really knows, right? So what you want to do is kind of keep track of their vital signs, even in the general ward or during patient transports inside the inside the hospital, or even for emergency response, right? So imagine that you have a mass casualty. You want to keep track of patients while transport is coming. So, I guess the motivation is that you want to keep track of these vital signs. Now, so from a technical perspective, the challenges that we're trying to address here is number one, reliability, right? So we want to obviously deliver again all the data. And also, in many cases, these patients are ambulatory. So, right, imagine the emergency room or in the waiting room, patients just walk around and we want to continue monitor their vital signs while they walk around. So what we built is a little mode called a MeTag, or Medical Information Tag, which is basically the same telos mode, but it has a little LCD that actually displays data and also displays messages. So nurses can send you pages to actually say, okay, please come back. And also has a little off-the-shelf Nellcore pulse oximetry sensor that monitors. It's a non-invasive sensor that monitors your blood or the level of oxygen in your blood and your heart rate. And these are two vital signs that actually can very quickly you can see whether a patient is deteriorating. This mode has a rechargeable battery, and then we do all this some duty cycling to make sure that we can have like 5-day lifetime using a battery like a iPhone battery. Now, the system that we kind of a very simple initial system that we built is something called Medicine, which is essentially combines these physiological monitors or MeTags that sample data and relay points. So what we do is that we go into the emergency room, and then we take these modes and we just plug them on walls, and then they create a wireless backbone that is used to relay data. And so this is, in a sense, one of the main interesting part of a system like Medicine, that we have this wireless backbone. So we use modes, but some of the modes are there to create a backbone, and having the backbone allows you to really control the reliability, because you can actually control, essentially engineer how your backbone works, and you can actually go and put more and more modes. And also it simplifies essentially the code, and improves the duty cycle of the little patient devices, because these guys no longer need to relay data. They don't really need to act as little participate in an ad hoc network, so they can aggressively duty cycle their radio. So I have run out of time. So this is so we deployed this system. So the main question is that, okay, what about reliability, as I said, right? So so this is my student John Cole that at the University of Maryland Trauma Center. So we did a pilot deployment at the University of Maryland and another deployment at the Hopkins. Monitored patients, and then using fairly off-the-shelf stuff, we can get fairly decent deployments even in very complex systems such as hospitals. Now here's some to kind of show you talking about benefits. So here's data from a patient, and here's a patient that is not feeling very well. So you see actually their oxygen level goes down, what is let's say 92%. And then you see actually their heart reacting as you would expect it to react. Actually, your heart actually starts beating faster to deliver more oxygen to your tissues. And then basically this is data. The point I'm trying to make is data that you would not be able to see otherwise, right? So kind of the benefit of a system like Medicine.
Does the moat know anything useful? Does the moat know that some data is more important? So it says, oh, this guy's sort of cool, so I'll just transmit less often, and this one, whoa, I really need to get somebody's attention.
Right. So again, we are at the point where we really want to basically collect data, and then working with physicians, it's not really a good strategy to tell them that you know what data is useful and what data is not useful, and then you will make that decision, right?
Ask them when it's important to get an urgent message. That's a different question.
Right. So basically where we are right now is saying that, okay, let's collect this data and then see if we can actually detect patterns where we can actually automate that process.
They want to tell you the pattern and then you can correct them.
Well, the point is that we don't have that data, right? So nobody was really basically measuring pulse ox at these rates, and in these types of patients, right? So that's where we are, very early stages. Yes.
Is there a reason why you didn't measure body temperature?
You would. It's not really the doctors tell us, not really, kind of a vital sign that you can actually use to predict whether a patient is deteriorating. But you could essentially have essentially another sensor that monitors body temperature.
But does it correlate well with the heart rate?
I mean, I don't know. I don't know, but I mean, if let me put it this way: if they tell me they need a temperature, body temperature, I would be glad to add it.
The same question.
Blood pressure is difficult. Blood pressure because you need essentially a pump to, and then battery basically becomes an issue, right? So, we are trying to, basically have another version that includes a BP sensor, a blood pressure sensor that does it potentially less often. And then you selectively deploy it on different patients that may need a BP sensor or may not need a BP sensor. So this is just, as I was saying, a research vehicle saying, okay, what can we do? And then, they later will tell us, oh, I want this sensor. Or in any case, there's more data that somebody wants to look at.
You also need location information because there are more.
That's the other nice thing, right? So Brano will be interested, and so we are starting to look at that. I mean, as you know, indoor localization is a non-trivial problem, right? So that's another issue. So I'm not gonna talk about a little bit about the future challenges. So. Number one, many of the system, I remember I showed you this picture in the beginning of essentially this loop. So the reality is that many of the systems that we have deployed so far are very much open loop. That is, you collect some data and hopefully sometime later somebody looks at that data. But we really want to essentially start reacting much sooner, and then maybe going back to the data center stuff where you can actually look at temperature and change. That's where things are going to start happening. Talking about the energy efficiency and going back to our discussion about how we actually download data, Koala actually doesn't keep the network active all the time, but at some points in time at least creates an end-to-end network to download the data. Now, however, when you create these n-hop paths, they are not efficient because if you think about how we actually send data, we cannot really use a link all the time because then basically it will start interfering with a basically upstream link. So right, we are actually, if you look at it, you may use a link a third of the time if you have a linear network. So basically, you're not really using the bandwidth very efficiently. And more importantly, because you have that radio on, and as I told you, keeping the radio on is basically the worst thing that you can do. Essentially, you don't really have the efficiency. Now, on the other hand, if you have networks that produce very little amounts of data, where in reality our network, our environmental monitoring network, really nodes collect a sample every 10 minutes. So we are thinking that we can use these beacons, these periodic probes that we were saying, that actually send data with your beacon. So basically, as you send the beacon, you also send the data. And then if you have, basically because you send many beacons, remember we send one beacon every 20 seconds, it might turn out that when you send your beacon, another node is actually awake, waiting to hear back from its own beacon, so you can actually push some data across. So you can actually create this network where the network is never on, but you still kind of use very efficient single hop communications to trickle in small amounts of data. So that's enough. So if this might sound like a delay tolerant or disruption tolerant networking to some of you. And finally, kind of a very different challenge is that as these systems become more and more mature, right? So people will actually, and we have seen this happening with TimeUS, where they actually contribute different protocols, right? So ideally so for example, let's say we have CTP, and then we have something like FTSP, right? So ideally what I want to do is that I want to take all these protocols and basically put them together to create my new application, right? However, the problem is that many of these protocols make assumptions that they actually have essentially exclusive use to the radio. So when you try to put them together, they start interfering with each other in unexpected ways. To give you some idea, imagine that I have a protocol that duty cycles the radio to conserve energy. So basically, and then you have another protocol that basically waits to receive a message. And the first protocol turns off the radio saying, okay, I am saving energy. The other protocol will never receive essentially the expected message. So you might say, okay, what I can do is that I can basically make sure that I can, I will check all these combinations to make sure that this protocol works well with that protocol. But by doing that, you're actually defeating the purpose of actually taking these off-the-shelf protocols and making them work together. So what we are thinking that it might be, you might want to provide this level of isolation where basically each protocol really thinks actually that it has its own little virtual radio, right? So this is maybe, so you basically, you give every protocol what it thinks is a virtual radio, but then you're actually sharing essentially the radio over the different protocols. So virtualizing the radio might be a way to actually achieve the desired level of isolation. Okay. So again, this is very kind of a very rough idea at this point, but I think it's an interesting direction. So before I finish, and I apologize for running over, I would like to thank my collaborators, Alex Saleh and Kathy Slavets at Hopkins, Ji Liu at Microsoft Research, and Richard Rothman at the School of Medicine. Razvan, Mike, John, and are my students, and Tia Gao works with us on the medicine project. And at this point, I would be happy to answer any questions. Thank you. Yes?
So most servers that I've worked with know what their internal temperature is.
That's a very good question. So, we looked at essentially onboard temperature sensors. And it turns out that these temperature sensors are very much correlated with actually CPU workload.
Can I just steal your
connector?
For more, please visit us at stanford.edu.